louder, but let's get feedback to see if you can either overshoot, right? Like overestimate, of course, not good with respect to environmental footprint. Of course, those costs will eventually be passed down to the customers anyway. And you don't want to under prepare either. That actually could cause loss of life. You could have prolonged outages with really unhappy customers. So these models have been, they're currently operational by a few different electric utilities and has helped them, cut costs in preparing for and responding to disasters. But these are, as you might imagine, sort of in a more shorter term, right? Like a couple of days out, a hurricane is approaching, a heat storm is coming, how to prepare for, and these hazard maps have been pretty useful to them. But how about, but you might say, hey, to be resilient, you want to think a little bit more longer term, right? Maybe you want to see which assets to better harden, make more resilient to actually for the next event, your system withstands it a lot more. And I can tell you that the same classes of models can be used. So just show you these are all the fun parts of, let's see. Yes, great. Maybe it's giving me an indication that be closer to the microphone. So I'll switch over here. So for the medium-term investments, again, a very data-intensive process, just like we talked earlier. You need to work very closely with geographers and climate scientists to get measures of, characteristics of the climate and geography of the area. You need information about the topology of your system, right? Like the topology of your power systems, the customer density, of course, characteristics of the hazard. So let me show the summary in a very ugly chart. But I want to say that, by the way, in these I keep forgetting, and I don't know why I got it to the other side. For these predictive models, we don't necessarily predict one measure of impact at a time. So, for example, in this case, look at where there is, the Y variable. Here I have outage duration, outage counts, and the number of customers affected. Now, these are the data sets I could get my hands on. In reality, for these metrics of impact, you have to really sit with stakeholders and communities and see, these things are never unidimensional, right? Like, what are the portfolio of indices that you care for? And then you build these rigorously validated predictive model that tells you what are the key risk factors. Now, you might say, hey, Roshi, are really decision makers interested in these black boxes where you throw a bunch of things in and you get some predictions out? No, actually, there's a good degree of explainability to these models. So, for instance, this is an example heat map you can get from this type of model. So, for instance, let me see. Oh, yeah, great. This works. So, for instance, you see trimming practices. Yeah, one of the key predictors of risk across all your metrics of interest. But for instance, if your the measures of topography of the system is more predictive of how many customers are left without power, but then the intensity of your hurricane is more related to the duration of power. So like you can show these maps to electric utilities and see, look, these are your key risk factors, but these are more important for whatever different metrics of interest. And by the way, you can show their partial dependencies as well. Again, the graphic is not very beautiful, but for instance, here it shows you like the less frequent your tree trimming, the higher your outages. Spend those dollars on tree trimming if it's beneficial for your system. But then the whole point was like, no, Roshi, you told us you wanted to develop models to inform investment decisions. Yes, then once you have characterized your key risk factors, right, and you understand the relationships, let's run what-if scenarios. So look at this heat map. It tells me tree trimming is really important. So let me go back to the service area, identify the grid cells that had really poor trimming practices and trim them, right, in a simulation, right? And then, of course, we identified 5 grid cells by the coast that pretty much all the assets were damaged. So we're like, what if we underground them? You rerun now this cross-validated model, and you try to see, okay, so for instance, one of the strategies, more tree trimming, the other one, undergrounding, what is the impact across all the metrics of interest for me? And so you see the reduction in impact, right? But one thing I want to point out actually is that while we do these multidimensional predictions, the electric utilities I work with, they do not care about these first two columns, right? All they want is outage number, so the number of assets damaged and the type of assets damaged. But look, for instance, if you're in a utility that you don't care about these two, and then you have these two measures, tree trimming, supposedly a lot cheaper than underground, then you see the impacts are pretty similar, right? So maybe I'll invest in trimming, even though, you know, the reduction impact is a little bit less. But look, the story across the customers that will be a lot different, right? So the whole point of, so we've done this work as a proof of concept of, look, when you do these risk and resilience analytics, you don't want to optimize for a single metric of impact, right? Like you want to work with communities and stakeholders and look across a whole portfolio of risk factors. And I'll show another example of that in a minute. But okay, so this is for medium-term investments. How about long-term, right? We talked about longer-term decisions, longer-term uncertainties. And again, we use the same simulation box, right? So you have a simulation model of your hazard and of your grid. And then of course, these are all the inputs that are all stochastic. So you propagate all your uncertainties related to your inputs through your outputs to see the impact to see the impact on your grid, but there is a whole new layer of uncertainty on top, right? Now, climate change could affect, right? Like there are different scenarios that could affect the different climate variables. The grid is evolving, the grid is modernizing, we are going to a completely different architecture. So then how do you credibly characterize those uncertainties, right, the epistemic uncertainties, and propagate them through the model? So one of the recent work that we've done, minus the topology change, so just looking at the climate change, is like, okay, so how is the climate change affecting the intensity, frequency, and landfall location of hurricanes, right? And so I encourage you, maybe if you have time, to take a look at this paper, because I think what we found is pretty interesting. What we found is actually that the outage risk under climate change is more sensitive to the uncertainty related to the frequency of hurricane. And that's interesting because in the engineering community, there's a lot of discussion of more category 5 hurricanes, more intense hurricanes that are important. But the reality is our current distribution system, the design load is not very high, right? So even a category 1 or 2 hurricane that sits on our system, it causes pretty devastating impacts on our distribution system. So I feel like, I believe these type of analysis are needed to actually inform the design criteria of our infrastructure if you want to climate proof or future proof our infrastructure. Now, pivoting a little bit, so this is, we talked a bit about risk framework to inform decision making. I promised some work around resilience. So maybe I'll show you one example project that we've done recently. But before getting started, we talked about definitions this morning. So what is resilience? Resilience, risk, sustainability, big topics, right? And people don't always agree on definitions. And this sentiment has been even stronger in my current position in the Department of Energy, right? Sometimes I feel like if you resort to one definition versus the other, it could be distracting on the kind of conversations that you have. So to sort of communicate my message to my colleagues in the policy world, I started drawing up from some of our intrinsic beliefs in certain concepts, as opposed to even published literature, even though they're pretty aligned. By the way, as a side note, I think there's a lot more agreements in the definitions than disagreements. But sometimes, for instance, what a conversation I hear a lot in my current agency is like, oh, but then we can't do it. So I've heard this actually by the Electricity Advisory Committee, is like, but we don't know, we still can't settle on a definition of resilience. So how can we measure it? Well, we know the fundamental pillars of resilience, and we can measure certain metrics of impact, right? But anyway, so one of my favorite quotes is the Japanese saying of resilience: fall down 7 times, get up 8, right? So get back up on your feet. Recovery is an important element of resilience. But then let's think of a Western equivalent of that. What doesn't kill you makes you stronger. I really like this actually, because what it gives you the message that resilience is not necessarily going back to where you started, right? You could actually end up in a better state, or maybe even, I mean, it might kill you, right? Like in a worse state. And so there is an element of transformation. And this is, instead of resorting to different clunky definitions, I've been trying to communicate to my colleagues that in the engineering world, we keep using resilience synonymously as recovery. We forget that there is a lot of transformation, that like the transformation element is an important one, especially if you want to consider the justice consideration, the sustainability consideration, right? I mean, there's so many examples in different cultures, right? Like this is a Persian sea monk rising from the ashes. I mean, sorry, this is not inclusive across all the cultures, but yeah, there are a lot of parallels in different ones. But I want to go so far as saying, at least in the engineering world, we've been having a very homostatic lens through which we observe systems, right? We expect things to be in system order X. There is disorder, your state Y. The expectation is you go back to X. But reality is we are always in the state of allostasis, right? You're in state X, disorder happens, and then you reorder, and state Z might not look exactly like the state X. Think of the global pandemic, right? I mean, we can have conversations about the rate of recovery across different parts of the world, different parts of the country here. But one thing we can agree on is like no sector, no nation went back exactly to what it was before, right? So there, like post-significant disorder, the reorder might not exactly look like what you started before. And I think this is an important consideration we need to have as we consider long-term sustainability and resilience goals. All right, so how do engineers view resilience? Actually, have you seen this resilience curve before? All right, so it's we like shapes, right? You know, on the y-axis you have system performance, and on the x-axis you have time. So there is disruption happens, your functionality drops, right? And then of course you recover. So the idea is you want to shrink this triangle. You want to not drop as much if you harden your infrastructure, or if you did drop, you want to go back as fast as you can. And as simplistic as this looks, this is actually pretty remarkable approximation of reality. So we've done a lot of mapping of real data post extreme events. So we've done a lot of focus on hurricanes because the data is really great. But yeah, it follows this resilience triangle pretty well. I mean, of course, not as smoothly, but great enough approximation. I don't have a problem with this. What I have a problem with is how abruptly we cut off the time. It's how soon after the disruption we want to characterize the resilience of the system. The reality is that the trajectory is longer, right? Like you can invest so that your recovery looks fast, but you're actually in a maladaptive state. An example is, I don't want to call out a particular utility company, but you know, spending billions of dollars to change the poles from wooden poles to steel poles, but then the design wind load is not the same. It's an overhead system, highly susceptible to extreme wind events. So yeah, maybe a transformative element would be more distributed resources that functions a little bit differently. But anyway, so my whole idea is like, why are we not considering the transformation element? And will it, by the way, tell us something differently or not? So I'll show you another proof of concept work we've recently done. So the first step, so this is a proof of concept done in state of Florida for Hurricane Michael, but now we are collecting larger scale data for different parts of the country to further validate. But the first step is that what we are using, basically the state of the art. So we are collecting a lot of data, basically all of the measures of socioeconomic variability that are considered in social vulnerability analytics. We have a deeply cross-validated predictive model. You identify the key risk factors and see if they're positively or negatively associated with your recovery. Here, recovery is restored access to electricity, right? So these bars show, how big of an effect they have on your predictive model, and then, whether they're positively or negatively correlated. So that's good. We have identified the key risk factors associated with power outages. By the way, I want to show you something really interesting. One of these is speaking Spanish, which is positively associated with restored access. And this is actually something that, so I was saying the power of data-driven techniques. In a lot of analysis, you see that there's quick conclusions like communities of color, very vulnerable, but there's actually a lot of nuances to these conversations, right? It turns out that it's not just necessarily once you control for socioeconomic factors, actually it's about community cohesion that sets apart communities apart. And the same story that we see here was in a large-scale analysis we were doing for the lethal extreme heat in Chicago that killed about 700 people in the 90s. Actually, the highest mortality after the African-American communities were on older, more isolated white communities, and actually the Hispanic community did really well. And again, the story there was like, there's a lot of social cohesion, self-organization that happens, and we don't consider that in our studies of resilience and sustainability and risk. And I think this is the beauty of data-driven techniques that help us tease out these more nuanced messages. But okay, so I have my key risk factors, right? So now I know what is positively associated with recovery, what is negatively associated with recovery. But then the next step is, as I was saying, like, we don't want to stop here at recovery. We want to find ways of understanding transformation. So how can we do that? We go to the main risk factors and we say, hey, let's consider if any of them are conducive to catalyzing or inhibiting transformation. And then we do a little bit of threshold analytics to identify that. So I'll tell you in a minute how we do that. So we have our risk factors. But then we built this, and I don't want to bore you. I promise it's right before lunch. So I'll say it at a high level, and I hope you pick up this paper later to take a look. But we developed an algorithm called contrastive community networks. It basically is built based on this unsupervised learning technique called self-organizing maps, which is a technique for simultaneous dimensionality reduction and projection. So what it does is that it builds a relational network of communities, right, where your proximity is based on the portfolio of risk factors. So you consider, we don't collapse the information into an average. We say, consider all the risk factors and then cluster communities based on similarity, right? And then we start perturbing these, risk factors, and we see how big of a change is it needed for this community to be mapped into an alternative equilibrium state, right? And then see if any of these key risk factors are conducive or so then, so we perturb and see if these community gets mapped into an alternative system, equilibrium. So we can characterize these transformation trajectories, but also see how much change needed for the risk factors. And I'll just give you the upshot. Actually, oh gosh, I'm running a little bit. Oh, sorry, a terrible. Great, thank you. So, I took a little bit too long because I might skip over some. I got too excited and I just didn't know what to present. Sorry about that. But yeah, so I do encourage you, if you have time, to take a look at this paper, because I think the results to me and my group were really interesting. Basically, what we show is that half of the predictors of recovery were found to be resilience traps. So like just a proof of concept to say, hey, perhaps we shouldn't just use recovery and resilience as interchangeable concepts. Transformation is increasingly important, right? Especially as we want to have justice considerations and so on. And we have the data, we have the techniques. Let's think a little bit more deeply about these elements. And maybe I don't go too much into what risk factors meant, partially because of time, and mainly also because, I think this is a really great proof of concept and we established a methodology, but I would really like the data to be a lot more larger scale, like more coverage across disasters and communities to feel a little bit more comfortable discussing the particular risk factors. But anyways, I know I'm a biased observer, but interesting paper. Please pick it up if you have time. All right, so then the second section that I might just pass by really fast because I really want to leave some time to interact with one another, is I talked an awful lot about hurricanes, but I'm not only obsessed about hurricanes. There is another extreme event which is being called the silent killer in the US, which I was surprised to see the statistics that is actually extreme heat has killed more people compared to all the storms combined. And this part of my work looking at the impact of heat on your demand for electricity and water started out of a collaborative. So I'm a co-author on the Indiana Climate Change Impact Assessment that started in 2018. So, it was like a multidisciplinary group of people getting together from the College of Agriculture, Engineering, Science, getting together to see the long-term effects of climate change on all infrastructure in Indiana. So my part was to sort of detrend the energy demand so that, of course, our demand for energy is a function of a lot of things, right? Like social demographic, technology, right? So like you remove all those just to see the climate sensitive portion of the demand and then see how that responds to climate variability and change, right? And as I started to dig into the literature to contribute to this report, it was fascinating. And it started a lot of different areas of research. It felt like we were putting a lot of different pieces of puzzle together, all pointing to the fact that the existing literature and practice is highly underestimating our climate sensitivity of demand for not electricity alone, but also water. And these are and actually we've done a little bit of natural gas as well. But so why? So I'll give you a few different examples. So the reason is, we assume a symmetrical temperature response of demand. So maybe I'll quickly talk about this. So this is a quantile regression of peak demand in PG in California, right? So you're relating the quantiles, the conditional percentiles of your demand to temperature anomaly. And what you see is that the higher intensity demand is actually more sensitive to temperature variability, right? So this is only the climate sensitive portion of demand. And by the way, the high intensity users are not necessarily the affluent segment of the population, right? There's a lot of literature that shows for instance, in Chicago, people who live in crime areas, right? They can't open windows for ventilation. They have higher demand. Lower social demographic communities or different labels, they live in more urban heat islands areas, right? Like higher demand, or more households occupying a home to save rent and so on. And by the way, and again, in the interest of time, maybe I don't dig in too much, but what we show is that when you consider future climate change, this sensitivity is even higher. So the amount that we are underestimating the temperature sensitivity of high intensity users is quite significant. Another thing is most of the existing research and practice, and I've been talking to a lot of utilities about this, they only consider temperature, right? Not humidity, which is a huge factor. The climate science is pretty clear, right? Like temperature is an inadequate measure of surface heat. A lot of important implications if you're considering climate change when you consider humidity. And we show a really large scale analysis across the entire US. And we show for each state, and actually I think maybe it was like a handful of less than 5 states where the sensitivity was similar, but for most of them, considering humidity was key, and not considering it was causing a lot of underestimation. And lastly, a lot of other factors, for instance, not considering the interdependency between the demand for electricity and water contributes to underestimation. And then, of course, the type of models that you use. So if you assume linearity, you have some really rigid, distributional assumptions and so on. So anyways, in a series of papers, we showed for various different reasons, we hope to sound the alarm, but not in a very doom and gloom way, because we can act, but we are, and the way that, the population is increasing, urbanization is increasing, the demand for critical services are increasing anyway, and yet we are even underestimating the sensitivity to climate. I think that's a big issue, and we've been putting out quite a few publications to highlight these and also showing them. So we've done projections for different scales, right, at city scale, individual household scale, regional scales, all pointed to the fact that, look, we are underestimating now. When you consider the climate change, the underestimation is a lot more extreme. We gotta factor these things as we are designing efficiency measures, right? Like, the technology goals that we are setting for increased AC penetration in the market. Let me skip over the data generation, so I was gonna talk, like, a big part of my research is, of course, getting creative with generating the data that we need at the scale that we need. So we've done quite a bit of work in that. I'm sorry about the flash. I want to get into the type of classes that I would be excited to teach. So as again, you've maybe guessed so far, the general areas of interest to me are extreme weather and climate events, the disasters, in general, the sustainability and resilience of infrastructure and communities, and of course, data-driven techniques for decision-making. Now that I've talked to, I've had some really great conversations this morning, I really regret not having a bubble here about life cycle assessment, environmental life cycle assessment. That's something that I think I'd be very excited to, if there is a need to contribute to. But I want to tell you a little bit about this class that I've been teaching. I've taught, I don't remember, 7 or 8 iterations of this class, and it was one of the most popular classes that I've taught at Purdue. And the idea is that the students design their own projects, right? So they, I tell them, the parameters of the design, and then they go and find real life data, and then they write a project proposal. I give them feedback, they complete their data collection, and then the idea is, like, with each new algorithm that I teach, they apply to their data set, and we work individually with students to work with them. And then in the end, so there is this big project that we get, and then very formal presentations, and then it gives me a very detailed feedback related to students. So like the most of them, a big portion of the students taking that class ended up in tech, and so that helped me link up with some recruiters, also know, like, how to provide feedback in a way that was accelerating their placement process. But then some of the really hardworking students ended up publishing their work. So I'll give you examples of the projects that they did in that class, and they ended up publishing in pretty great outlets. For instance, looking at the global environmental sustainability, right? Like, the idea is, people usually look at how environmental sustainability indices change over time. But the problem with that is that those indices are not calculated exactly the same way across the years. And then a lot of things that go into those metrics, shift over time. So we were doing a completely different framework of, like, similar to what I was showing with the transformation and resilience, like mapping countries according to their similarity in their risk environmental sustainability portfolio, and see whether they were moving, the portfolio was moving in a positive or negative trajectory. And then a host of other work related to renewable integration challenges that, unfortunately, due to time, I didn't manage to talk about. But in general, I am hoping to be cognizant of the pillars of impact that might be of importance here. And of course, we are in the research world, we are all dedicated to science contribution, right? Like, so we want to put out the best papers out there. So we've strived to have publications not only in disciplinary journals, that to me is reliability engineering and risk analysis, but also interdisciplinary high impact journals, to make sure a broader community of people are picking up the work. But as you can tell by my decision to do my sabbatical in a non-academic institution, I've been more and more seeing impact as engaging more closely with people of policy and practice, right? And you know, more recently, I'm writing more for industry outlets, you know, opinion pieces, trying to learn ways of communicating my work better with policymakers, because I'm getting disillusioned by the fact that, you know, some of our papers, great work going to them, they sit on the shelf and nobody picks them up. And now I'm learning people of practice and policy don't go and read your papers. We have to find a more creative way of getting our work. And one of my most recent experiments was playing around a little bit with the NSF I-Core program, and we are trying to pursue an SBIR, you know, just trying to find pathways of getting your research into the market, into the policy, into the practice. And of course, you know, with respect to professional engagement, you know, I go to a range of different conferences. I would love to learn what some of the conferences of interest to the colleagues here are. The core one that I've never missed once over the past, I don't know how many years, is the Society for Risk Analysis, where I'm the chair of the Science Committee and the Education Committee, and I've sat on the council. But the key element for me is the mentoring. So that the big piece that, you know, as I am I'm still on leave from Purdue, but still interact with students. But in my current role, even though there is some element of mentoring, that's the biggest piece of job as an academician, that if I were not to do it, I would dearly, dearly miss it. And that's the one that I value above most. But I have also been extremely fortunate with the students that I've worked with. So just some examples of my former graduate mentees, 3 of them in Amazon, and then, sorry, Jackson has recently moved, so I don't remember, but the Debs is in Capital One. And then my former PhD students and postdoc currently in Research One institutes as tenure track faculty. And my current students, of course, unfortunately, I have had to have a leaner mentoring portfolio because of my engagement outside academia. But the student on top is currently a Fulbright Fellow, enjoying life in New Zealand, and he's being co-advised by a colleague in urban forestry. And well, Steve is very much into algorithms, operations research, and tech, so he's staying within industrial engineering. And last but not least, I wanted to say that mentoring has been basically what drives me as a researcher and grounds me as a researcher. And wherever I've had the privilege of having some sort of platforms, whether as a graduate student at Johns Hopkins, faculty member at Purdue, you know, through my engagements in professional societies, and currently at the Department of Energy, I've really tried to at least do my piece. However, I think I can do best to broaden the participation of underrepresented groups. That means a lot to me. And and if colleagues have feedback, you know, success stories, I would love to hear, because that's the part that I get, you know, the rewards of the job, let's say. And finally, most of my research has been funded by various programs within NSF, some interdisciplinary institutes at Purdue. And, you know, I just have a cartoon here because I'm not allowed to say there's a lot of non-disclosure that comes with working with utilities. So clearly you can't guess which utilities I worked with. But yeah, they've been partially funding some of the work. And last but not least, what a beautiful campus. And actually, I'm going to take advantage of this beautiful day to walk around a little bit. But what I love about you guys, we were talking earlier today as well, is like, you know, I've been navigating my life or my research life as an interdisciplinary researcher across various different departments, right? And no matter how dedicated to interdisciplinarity many universities are, there's still a lot of legacy barriers. And I'm just so excited to see such diverse group of scholars that are bound by the shared mission as opposed to disciplines, which is something that typically happens. And secondly, of course, your location, right, being close to our policymakers is something I don't take for granted. This is not the privilege that many universities that are outside the capital have, and that's actually a huge, I think, huge resource. And last but not least, what I've been learning so far is the fact that you guys are growing and building things from ground up, being part of that vision. It's so exciting. I've been very inspired by everything that I've learned so far. So regardless of what happens in the future, I hope to find ways of collaborating with this really amazing group. And with that, I'm sorry I took longer. Sometimes I get off tangents. But I hope to get your feedback. Hope I managed to confuse everybody. Questions?
Yes.
Sure. What an amazing collection of work that you shared. Thank you so much for this excellent talk. I'm really interested in the energy sort of sustainability of energy systems. These two types of extremes that you talked about. Be less shorter, more localized hurricane extremes versus heat waves that span the entire grid and last for multiple days and are getting. Yeah. How do you think about the resilience? Like, how are there things to do to make the energy grid more robust and heat extremes?
Yeah, no, what a great, excellent question. And actually, you're pointing to the fact that why I focused in the beginning so much more on doing hurricane related work, right? Because it's a lot easier to do work when your spatial temporal scales are a lot more constrained and where things are a lot more defined, right? Like even heat wave, right? Extreme heat, the definition is not consistent, right? There is no definition. Again, we go back to nobody agrees, but yeah, like there's a lot of variations. And the other piece of it, which actually excites me, and it's going to be a growing area of my research lab, is the risk of compound climate risk are increasing, right? So it's not just necessarily the heat wave with a drought on top. How does that impact your, and then multiple droughts happening in different areas of the country? Our energy sector are very much interconnected. So there's a lot of complexity that is, so like we are, to your question, that's why I was showing the picture of the puzzles. Like we started with baby steps, right? Like let's see how your demand responds. So now one of my students is actually recently worked on the response of generation, right? But then thinking of interlinkages within the climate system and how it propagates through the energy system is not a trivial question, but really exciting. And then that's something that actually I'm learning on now this side at the DOE, that the national labs are building this large-scale model called NARM, North American, it's a fancy acronym for North American Energy System. I don't remember the details. And they're trying to incorporate a lot of data and networks to be able to characterize these interdependencies. So I think engaging with that effort to build out different pieces of that is going to be key. But what a great question, and the answer is I don't know the answer, but you're trying. You're taking baby steps in that direction. Thanks for asking that. And sorry.
So as the grid is shifting from to renewable sources, does fundamentals of the risk analysis change, or does it remain the same? Or just how different is it?
What a really, really good question. So and this is something that I spend quite a lot in my current agency. A lot of the fundamentals of the grid is changing, right? So like a lot of power systems considerations are changing, right? Like the way to do stability of and there's a lot of really good research done that way. But and I don't remember who I mentioned to this morning that I recently wrote a congressional report related to education pipeline for grid modernization. So what are the curricular activities needed to support this grid modernization? And I was one of the key points were integration of risk science within the curricular activity, because traditionally grids could be run very easily by system engineers, right? But now the stakeholders are changing, right? Like customers we are getting prosumers, right? Producing consumers. So there you have to consider now social behavioral sciences are of considerations. Now we have cyber attacks. Now we have extremes. Right, the old way of being in control of your grid no longer works, and we need more so that the fundamentals of risk science doesn't change. But we need more foundations in risk science to apply those fundamental principles to make sure we don't just get bogged down by the stability issues here and there, but consider the fuller picture in transition. But what a great observation. Thanks for asking that.
I was wondering how adaptive your predictive models are with regards to, say, one county hardens its infrastructure, another sort of divests or for whatever reason doesn't recover properly. How quickly do your models respond or deliver information to managers, and what does that sort of network look like in sort of
that's also like very observant crowd. I appreciate you asking that question. So the first thing is but besides that all models are wrong, some are useful, garbage in, garbage out, right? So the one thing that I want to be very clear, actually I maybe didn't mention that some of these models that I talked about are predictive models, some are physics aware simulation models, right? With the predictive models, exactly, what a great observation. If the dependencies or if the architecture of your system changes, the output is garbage, right? So because you've characterized the dependencies between your inputs and outputs, but then some of those dependencies are shifting. There is architectural changes. So please throw out that predictive model. And that's why and that's another thing I failed to mention. And a lot of these, with the even predictive power outage risk models, I worked very closely with structural engineers as well as climate scientists to make sure the statistical models encapsulate the physics, right? So like a lot of our design wind load of infrastructure is reflected into those models. Now, for if you have a physics-based models, you don't have that issue, right? Now, how fast you can reflect those into your different types of simulation platforms you have. It depends on how accurate of the model you want to have, right? Like we can talk about sometimes you want like a back of the envelope calculation, or you want a very elaborate prediction of what might happen, right? And there are different strategies that but in short, I would say, yeah, predictive models, not the answer. Physics-based only models, not the answer. Maybe marrying them together and being very cognizant about epistemic uncertainties, unknown unknowns, known unknowns, underlying assumptions that we are not always very good and transparent about them. But yeah, so sorry, a roundabout response to a very good question, to the on-point question.
Okay, well, let's thank Roshi again. Thank you.